Beam area. Beam area is a solid angle through which all the power radiated by the antenna would stream if power maintained its maximum value in theta and phi direction over a sphere and was zero elsewhere. The radiation intensity P of theta phi should be maintained constant and maximum throughout the solid beam angle, its value being zero elsewhere. So power radiated is given by P of theta comma phi or a sphere in watts. The radiated beam of the antenna comes out from an angle at the antenna known as solid angle, where the power radiation intensity is maximum. This solid beam angle is termed as the beam area. It is represented by omega A. It's a solid angle. Beam angle is a set of angles between the half power points of the main lobe. Therefore, beam area is given by integral of the normalized power pattern over a sphere. If I expand this, it's a integration phi 0 to 2 pi and theta 0 to pi. Normalized power pattern in d omega, which is in steradians. Figure shows the incremental solid angle dA on the surface of the sphere. In polar two-dimensional coordinates, an incremental area dA on the surface of a sphere is the product of the length r d theta in the theta direction and r sin theta d phi in the phi direction. Thus, dA is equal to r d theta r sin theta d phi, which is equal to r square into d omega, which is a dA, where d omega is solid angle expressed in steradians or square degrees. So d omega is a solid angle subtended by the area dA. The area of the strip of width r d theta extending around the sphere at a constant angle theta is given by 2 pi r sin theta into r d theta. Integrating this for theta values from 0 to pi yields the area of the sphere. Where when I integrate this 2 pi r square integrate 0 to pi sin theta d theta, so which is equal to 2 pi r square which is equal to 2 pi r square sin theta integration minus cos theta 0 to pi which is equal to 4 pi r square, which is a area of sphere. Where 4 pi is solid angle subtended by a sphere in steradian. One steradian is equal to solid angle of sphere divided by 4 pi, which is equal to 1 steradian is equal to 1 radian squares, which is equal to 180 divided by pi square unit degree square. So therefore 1 steradian is equal to 1 radian square, which is equal to 3282.8064 square degrees. Therefore 4 pi steradian is equal to 3282.8064 multiplied with 4 pi is equal to 41,252.96, which is approximately equal to 41,253 square degrees. Is equal to solid angle in sphere. Therefore, the beam area or beam solid angle of an antenna is given by the integral of the normalized power pattern over a sphere. So I can write this as an integral over the normalized power over the sphere in steradians where d omega is sin theta d theta d phi steradian. The beam area of an antenna can often be described approximately in terms of the angles subtended by the half power points of the main lobe in the two principal planes. Thus, beam area can be expressed in terms of half power points in theta direction and phi direction. Theta HP and phi HP are the half power beam widths in the two principal planes, minor lobes being neglected. Radiation intensity. Radiation intensity or the antenna power pattern in a given direction is defined as the power radiated from an antenna per unit solid angle. The radiation intensity is a far field parameter which can be obtained by simply multiplying the radiation power density by the square distance. That is, r square into half real value of E theta and H phi, which is equal to r square into half. So real value of the E theta H phi I can write by this equation also, E theta divided by Z naught. The relationship between the total power and radiation intensity is given by integral of u d omega, that is 0 to 2, phi is 0 to 2 pi, theta is 0 to pi, u radiation intensity d omega, which is equal to phi is equal to 0 to 2 pi, theta is 0 to pi, u d omega is sin theta d theta d phi. Radiated power for isotropic source is given by phi is equal to 0 integral of the radiation intensity of the isotropic source theta is equal to 0 to pi, which is equal to 4 pi u naught, where d omega is equal to sin theta d theta d phi. Therefore, radiation intensity of isotropic source is radiated power divided by 4 pi. Normalized power pattern can be expressed in terms of radiation intensity, that is ratio of the radiation intensity in theta and phi divided by radiation intensity, maximum value of the radiation intensity, which is equal to ratio of the pointing vector to the maximum value. Radiation intensity of the isotropic source is independent of theta and phi. Beam efficiency. The beam efficiency states the ratio of the beam area of the main beam to the total beam area radiated. The energy when radiated from an antenna is projected according to the antenna's directivity. The direction in which an antenna radiates more power has maximum efficiency, while some of the energy is lost in side lobes. The maximum energy radiated by the beam with minimum losses can be termed as beam efficiency, which is given by beam area of the main beam to the total solid angle. Total solid angle is given by beam area of the main beam plus beam area of the minor beam. Stray factor is given by the equation minor beam area of the minor beam to the beam area, total solid beam angle. Therefore, sum of the beam efficiency and stray factor is equal to 1. Directivity and gain. The directivity of an antenna is defined as the ratio of the maximum value of the power radiated per unit solid angle to the average power radiated per unit solid angle. Directivity is a fundamental antenna parameter. It is a measure of how directional an antenna's radiation pattern is. An antenna that radiates equally in all directions would have effectively zero directionality, and the directivity of this type of antenna would be 1. Gain is inherently directional. The gain of an antenna is usually measured in the direction which it radiates best. Directivity is a component of its gain. If lossless antenna, gain is equal to directivity. The ratio of radiation intensity in a given direction from an antenna to the radiation intensity averaged over all directions is termed as directivity. If the particular direction is not specified, then the direction in which maximum intensity is observed can be taken as the directivity of that antenna. The directivity of a non-isotropic antenna is equal to the ratio of the radiation intensity in a given direction to the radiation intensity of the isotropic source. Directivity is expressed by the expression ratio of the maximum power density to its average value over a sphere. Consider the equation 1. Directivity is always greater than or equal to 1 and it's a dimensionless value. The average power average power density over a sphere is given by the equation 1 by 4 pi integral for a phi 0 to 2 pi theta 0 to pi integral of the power over a sphere d theta d phi, which is equal to 1 divided by 4 pi integral of the power in theta and phi direction over a sphere, watts per steradian is a unit of the average power density over a sphere. Equation 2. Substitute equation 2 in equation 1. Directivity is equal to maximum power divided by average power. This is the first equation. So average power is substituted to the expression integral of the power over a sphere into 1 divided by 4 pi. For directivity is equal to, I can write the above equation by 1 divided by 1 by 4 pi into P of theta of pi divided by P of theta phi maximum d omega, which is equal to 4 pi divided by ratio of the power to its maximum power is a normalized power pattern. into d omega, which is equal to 4 pi divided by integral over the normalized power pattern over a sphere is a beam area. It's a directivity from beam area is 4 pi divided by omega A, where normalized power pattern is equal to ratio of the power pattern divided by maximum of it power pattern. Directivity of the antenna can be measured if the half power beamwidths of the antennas are known, which is the equation given by 41,253 square degrees divided by theta hp into phi hp, where theta hp and phi hp are the half power beamwidth in theta plane and h plane respectively. So directivity, therefore approximately I can write 40,000 square degrees divided by theta hp in degree and phi hp in degree. If the antenna has a main half power beamwidth is 20 degree in both principal planes, its directivity is 40,000 square degrees divided by 20 degree into 20 degree, which is equal to 40,000 square degrees divided by 400 square degrees is equal to 100 or 20 decibels. The gain of an antenna is an actual or realized quantity which is less than the directivity due to ohmic losses in the antenna. In transmitting, these losses involve power fed to the antenna which is not radiated but hits the antenna structure. A mismatch in feeding the antenna can also reduce the gain. The ratio of the gain to the directivity is the antenna efficiency factor. Thus, gain is equal to K into directivity, where K is efficiency factor. Which is always 0 between the 0 and 1 and is dimensionless. Gain is always less than directivity. Gain is equal to directivity for lossless antenna. Gain can be measured by comparing the maximum power density of the antenna under test with a reference antenna of known gain. Gain is equal to maximum power of the under test antenna maximum power of reference antenna into gain of reference antenna.